Hi everyone, I'm Dan Fullerton and I'd like to talk to you today about Atwood machines. Our key objectives here are going to be to introduce students to the idea that tension is constant in a light string that passes over a massless pulley, and you should be able to use this fact to analyze the motion of a system of two objects joined by a string. Secondly, we want to solve problems in which applications of Newton's laws leads to a couple simultaneous linear equations involving unknown forces or accelerations. And these are consistent with the AP Physics B and AP Physics C objectives. So, we'll do this in the context of an Atwood machine. So what is an Atwood machine? Well, really an Atwood machine is a lab apparatus, an experimental setup, in which two objects of mass m1 and m2 are connected by a light massless string to an ideal massless pulley. The properties of an Atwood machine allow us to do very simple calculations. The pulleys are ideal, they're frictionless, they're massless, and therefore they add no inertia to the system. And the tension in the light string over the ideal pulley is constant. That means the tension at that point in the string must be equal to the tension at that point in the string. And we can say that because of the assumptions we've already made. So how do you set up these kinds of problems? Well, the first step is to decide a direction you want to call positive. And because you've got one object moving up and one moving down, what I like to do is I like to pick one consistent direction like we have here and call that the positive direction. We'll use plus y in this case, and I'll go having m1 go down because it looks to me like m1 is bigger. So we'll start off with that assumption. Anything on this side, on the right-hand side that's moving up is positive. Anything over here on the left-hand side that's moving down is positive. Now what we can do is we can analyze each mass separately using Newton's second law and free body diagrams. So as we start this, let's do a free body diagram for the mass 1. I do m1, there it is, m1. I have some tension in the string T upward, and I have the weight of mass 1, m1g, downward. And note, in this case, on the left-hand side, plus y is down. On the other hand, if I go do a free body diagram for mass 2, I have mass 2 here. Now I have tension pointing up again for mass 2 and m2g down. But in this case, we're calling up the positive y direction. So from here, I can start writing Newton's second law equations. We'll start with the one for mass 2. Net force in the y direction, looking at just mass 2, is going to be t in the positive direction minus m2g, and that has to be equal to mass 2 times acceleration. Or if I rearrange that to solve for tension, tension is equal to mass 2 times acceleration plus mass 2 times g, the acceleration due to gravity. We'll call that equation 1. Now I'm going to go back to mass 1 and write Newton's second law equation. F net y for that first mass, I have m1g in the positive direction minus t, and that must equal m1a. Therefore, I can write that as m1g. My tension, I know, is m2a plus m2g. So I can substitute in t with m2a plus m2g, so that becomes minus m2a plus m2g equals m1a. Therefore, m1g minus m2g equals m1a plus m2a. What I'm going to do now is rearrange this to solve for the acceleration. So what I can do here is say then that I can pull a g out of the left-hand side. G times m1 minus m2 must equal a times m1 plus m2. We're solving for a by itself. A equals g times m1 minus m2 over m1 plus m2. I've solved for the acceleration of the system. There's an alternate way that we can solve these, though. Let's take a look. If I analyze the system as a whole, let's call the entire system both of these masses. We've still got our positive direction set up to the left, And what I can do is by drawing that dashed line around the system, a closed system, because it's a closed dashed line, I can write Newton's second law directly, realizing that I have a couple forces to deal with here. M1 is going to have M1g pulling this way in the positive y direction. M2 is going to have M2g pulling this way in the negative y direction. So if I go to write my Newton's second law equation right away, net force in the y direction is going to be M1g over here minus M2g, and that has to equal the total mass of my system, M1 plus M2, because I'm looking at the system as a whole, times the acceleration of the system. Now it's a pretty easy rearrangement. I can pull g out on the left-hand side. G times M1 minus M2 equals A times M1 plus M2. Or, again, solving for A equals G, M1 minus M2 over M1 plus M2. Same result, just calculated in a different manner, using that alternate method, looking at the system as a whole. So hopefully that gets you started with Atwood machines. If you need more help or are looking for more information, check out aplusphysics.com. Make it a great day, everyone. Thanks.